quantum model. In other words, what the heck is going on with chemicals and atoms that makes them do the sorts of things that they do. Okay, first of all, we're going to begin at a point where a lot of people don't even consider chemistry actually being chemistry, which is to say we're going to go historically back to a situation where we used to take glass tubes filled with either sometimes nothing and sometimes filled with various gases, and we would basically apply electrical current across or through those gases. And this is a little demonstration of that particular device. There's a glass tube with some wires on either end, and this guy's going to throw the switch. And what happens? We end up with this glowing tube releasing light because electricity or electrical current is passing from one end through to the other. Incidentally, this end here is called the cathode, and because the ray appears to come from here to here, we call it a cathode ray tube. So again, important idea here is that what we're trying to explain is the behavior of chemicals and atoms in a cathode ray tube. That was kind of like the big kind of crucial experiment that kind of made everything start to change. So one of the things we did with this light was we wanted to capture the light and kind of separate it and filter it. And the easiest way to filter light we've known for hundreds of years is by using a glass prism. So we would take this glass prism and grab the light coming off here in a dark room, and we would separate the light. We'd separate the light using this prism. And now I'm going to show you some of the results that we would get. So for example, if we were doing that with just air, we would get this sort of appearance here. And the funny thing is we would get these gaps which just really didn't seem to make sense. So again, the chemistry people were like, how can we explain this? How do we explain the behavior of atoms and chemicals? How do we explain this behavior? Because we're shooting electrons or energy, electron energy through these gases, and this is happening. How come? And we do the same thing with oxygen, and we get a completely different appearance. We get a thin green band here. I might be able to pop that up. We get a little bit of green here. We get a little bit of blue here. We even get a little bit of red over here. But we have all these big black bands. And notice that there's a very specific color of green. I'll show you another one. So, then the chemistry people are saying, well, let's try something else. So let's try nitrogen gas. And we get that particular thing there. Well, what about if we try hydrogen gas? Well, we get this particular spectra, or what we call emission spectra, released. So we see these particular colors, and I really hope that you can see that. So let me just move this over just a little bit, and we'll zoom in a little bit bigger. So we get this band here, this band here, this band here. So the scientists, the chemists, and the physics people are all trying to explain that. And not surprisingly, they end up having to do a whole lot of arithmetic and math. The three major explanations are known as the Bohr explanation, the DeBroglie explanation, and the Schrodinger explanation. So now I'm going to grab this simulation. In here, there's a PHET simulation. And if we grab and run this PHET simulation, we're going to see how that works. So we'll start off and we'll say, what does the Bohr model predict? So this simulation of a simulation is, we're going to turn this thing on, and by turning it on, what we're saying is that we're going to shoot light through this hydrogen thing, and we're going to wonder exactly what's going on. So let me just poo-head. Here we go. Let's try that. Alright, here we go. So we're going to turn this on, and this is a simulation of the light or the electrons, for lack of a better phrase, shining their way through or burrowing their way through a container of hydrogen gas. And so the Bohr model, he basically said this is what's happening inside an atom. We've got these rings, we've got these orbitals, and some of these electron particles or light bump into the electron, which moves from one energy state to another, and all of my theories predict that what we're going to get is specific wavelengths of light being reflected or coming off that cathode ray tube. And what I've got here is I've ran that same simulation for quite a long time. So this simulation says, or at least the Bohr explanation says, we're going to get red light, cyan, a little bit of blue, and a little bit of violet. And if we compare that to what actually we get here, it's kind of interesting to see the similarities that we get. So in other words, this is Bohr's explanation, and Bohr's explanation almost perfectly matches what's happening. And that's to say that his equations also explain almost or match almost exactly what's happening. But of course there's other ways to explain things as well. So if we pop over to the DeBroglie explanation, and I'll show you what that looks like on the simulation. So we'll take this out of the road here, and we'll go back to our simulation here, and we'll say, okay, let's go to the DeBroglie model. Same idea with the DeBroglie model, except that he's talking about these weird nodal vibration wave thingies. And let's just speed this simulation up. And notice that the DeBroglie model is still predicting certain wavelengths of light coming off, and not surprisingly I ran that for a few minutes for you. And we end up with this result here, and you're noticing, look right down in here, and we'll compare this to what we actually see. So what you see up here, what you see here is that's actually oxygen. This would be hydrogen here. There we go. So there's the hydrogen spectra that actually results, and you can see that the DeBroglie model almost exactly matches the results that we actually get. And of course there's a third model called the Schrodinger model. Let me just make this go away. And we'll pop open the Schrodinger model, and we'll run the Schrodinger model. And why can I not run the Schrodinger model here? Click. There we go. So the Schrodinger model has similar sorts of ideas. We're going to run this as well, and when we run that for a while, we'll end up with this as our final result, which we'll compare to the actual hydrogen spectra, and you can see that we've got a match here, we've got a match here. Interestingly enough, the Schrodinger model predicts something in around here that we're not necessarily seeing, and well, we couldn't see those anyways because those are infrared and they're invisible to our eye, and these are ultraviolet, so they're invisible as well. Okay, big ideas here. Here comes the summary. 3 different models for explaining what's happening in atoms. And remember, explaining the big explanation we're trying to come up with is why is it, let me just stop that. We're trying to explain why is it that when we excite atoms or chemicals with electrical energy, why do we get these very strange emission spectra? 3 different models. The Bohr model, and the DeBroglie model, and the Schrodinger model. They're all quantum-based models, and they're all models that actually explain these particular phenomena. And so understanding quantum theory involves understanding how those explanations work and being able to work with those explanations.